In this video, we'll be going over an example of simple linear regression. This is assuming some familiarity with a simple regression problem, at least seeing it at one point and not being completely oblivious to jumping in a problem without getting some background information. We won't go into definitions or anything of that nature, and the following data comes from onlinestatbook.com. So we'll start with the problem right away. Here, suppose x represents the number of hours shopping and y represents the number of US dollars spent in hundreds. And I'm going to list these data pieces in an XY chart. 1, 2, 3, 4, and 5. And then 1, 2, 1.3, 3.75, and 2.25. So here, the in hundreds is important because it'll make sense in terms of the numbers I've used. They may have a different story on this website, however, this seems a little bit more relatable if you're talking to a bunch of students. So the first one, 1 for 1, it's 1 hour for 100. 2 for 200, 3 for 1.300, but nobody speaks like that. So that would be 130, right? You move the decimal 2 places. Now when you're given information like this looks like it's not much of a problem, but what we're going to do is we're going to go through an uninterrupted process of all the steps that are involved with a simple linear regression problem, and I'll type them out and explain them as we go through them. So first part A generally, is asking you to plot the data or create a scatter plot. It depends on who you're talking to. So in this case, you wanted to make a nice visible XY coordinate plane. And the nice thing about these numbers is that we can go by ones. So there's 1, 2, 3, 4, and 5. Same here on the y-axis, 1, 2, 3, 4. We can go as high as 4, that's fine. And we simply plot each one. So I'm going to take the time to do this. So there's 1 and 1, 2 and 2, we have 3 and 1.3. So of course this isn't drawn super to scale, but you want to approximate the best you can. So 1.3, it's a little bit under half, so maybe a touch right there. 4 and 3.75, so you know that's closer to 4, about right there. And then 5 and 2 and a quarter, so 2.25, so that means closer to 2, so something like that. So here, as you can imagine, and the point of this all is that, well, of any regression problem, is you're taking raw data, in other words, information that you have collected or sampled or whatever your favorite phrase is, and you're taking those pieces of information, you're trying to create an equation or a regression equation that best represents not only the data that you've recorded, but any future data that you're going to collect. So that means that someone can walk in and go something insane like, I spent 6 hours shopping today. How much do you think I'm going to spend? So based on these data points of five persons, as you can imagine, you're going to create some kind of equation. You can see that here, I'm going to draw this but not keep it here because it's only an estimation. You can see that you would imagine the regression line go in some kind of upward trajectory like that. Now the data won't always suggest that, it just depends on the problem. So here we're just plotting the data, and that's that. Generally the second step though is to find what that actual regression equation is. So you'll normally get something like find the regression equation. Now, depending on which textbook you're looking at, I've come to use this equation because it's quite standard. It's not the standard, but you get y hat equals beta 1 x plus beta naught, or beta 0. And what happens is that this is, of course, the general equation for a simple linear regression. One variable, right? That's why there's one x. If you're looking for multiple regression, if I ever get around to making a video of that sense, then we can discuss how there can be a generic equation written for extended variables and whatnot. But since this is simple linear, we can keep it nice and simple like that. And as we're finding this equation, it's not simply of finding the constants, or in statistics terms, or statistical terms, the weights, the beta 1 and beta naught. Those, sadly, come with complicated formulas. They're not difficult, they just are really messy. And what happens is that once you understand them a little bit more, you'll recognize them a lot better. So I'll write down those formulas again really quick just for reference. They don't come from anywhere special because someone's taken the time to construct these equations, so no need to talk about that. And here's the beta naught. Now the first thing you'll notice once I'm finished writing these equations out is that the denominators are the same. They're the same exact ones. So in fact, I'm just going to write same here to make your lives easier. Okay. Now you'll notice all these summations. Now I've taken the liberty to, in advance, calculate these summations. This is something you would be doing by hand. And it could get tedious, it's just you want to be careful, but again, this is assuming that someone's already familiar with simple regression and knowing that the summations are involved. So let me write down all these numbers for you. So that's the sample size, right? Then we have the summation of x, which is 15, summation of x squared, which is 55, summation of y, which is 10.3, summation of y squared. No, sorry, I misspoke. xy, there we go. 35.15, and summation of y squared. Now this is the one I wanted to refer to actually, 25.815. I'm going to be putting a little asterisk here, and you'll notice if you pause the video or you're looking at this at any future date, you'll notice that there's no y squared component or summation of y squareds here, and that's because it is involved strictly with the correlation coefficient, or in other words, R, or multiple R, depending on who you're talking to or which textbook you're reading. However, the way I've been teaching this is that if you're going to take the time to do 1, 2, 3, 4 summations, what's one more summation? You can have it all written here to your advantage. Okay, so just a heads up there. So now I'm going to write down the beta 1, or in other words our slope first, with the numbers plugged in, and then I'll talk about a couple of key components there. So I'm just scrolling down a little bit. I'll put the beta 1 equation on the far left side so it matches the format of this here. So the beta 1, using those same summations, right? 5 times 35.15 minus 15 times 10.3. This is all over the denominator, 5 times 55 minus 15 squared. Now, of course, again, you would want to take the time to calculate the denominator and the numerator separately. I wouldn't break it out as taking, for example, 5 times 35.15 in the numerator minus 15 times 10.3. I would punch that all in the calculator at once, because your calculator will know to distinguish order of operations and to do the multiplication before the subtraction. In this case, though, you'll have 21.25 in the numerator and then 50 in the denominator, and this comes out to 0.425. So this is the number we're going to be using for beta 1. Now, rarely the numbers come out this nicely. This is actually a decimal that doesn't have a non-repeating pattern. Normally it will be 0.42567311010, whatever the case may be. So this one's a nice simple one. They rarely come out that way, so don't have that expectation. And beta naught has this denominator, 10.3 times 55 minus 15 times 35.15. And remember, I took the time to say like, hey, this is the same. So you just plug in this 50 again. Don't kill yourself, right? Don't take the time to realize that you have to make another calculation of some sort. This will give you less opportunity for error and will make your life a lot easier. So this number turns out to be 0.785. So here, your beta naught is this number. Using both of these numbers together, we get a y hat equal to 0.425x. Don't forget the x, I generally do that. 785. Now, just something to note is that both these numbers can be negative. It depends on the problem being asked. In this case, we should recognize that there should be a positive slope as well as intercept, because if you scroll up and you look at your points, you know that any kind of regression line that's going to piggyback off of these points is going to go to an upward direction. And what will happen is that if you're going in an upward direction, you must have a positive slope. Okay, so again, I know I made this look seamless. However, one would want to take the time to calculate summations and go through this process. Okay. Now, generally, what we have is we gotta plot this equation 0.425x plus 0.785 onto the graph that we had earlier in part A. However, what I generally do is I make people find the predicted values. So this would be part C, and the purpose of this is to easily graph your graph, in other words, or your equations more specifically. So I would say find the predicted values for spending 0 and 1 hours, or 1 hour respectively, shopping. Basically, this is what this is asking you to do is find y hat for x equaling 0 and x equaling 1. That's all. It's just a contextual way of saying it. So in our case, I'm going to write y hat 0 so that we know. Actually, I'll even put that in a different color. Y hat 0 because we're going to plug in 0 for x. And we get 0.425 times 0 plus 0.785. So of course you can do this and you get an answer of 0.785. But what I would tell students to do is write this in a point format so it's easier to recognize. So there's that. And then y hat, but we're going to plug in a 1 this time. We're going to have 0.425 with a 1 plus 0.785 equals equals 1.57. Again, I would take the time to write this as 1 comma 1.57. So those are the numbers right there. They're simple calculations. This is the traditional where you're given an equation and given points and you plug it in and you get the value. But not only do you do that, excuse me, you are also going to use these points for part D. And part D generally asks you to graph the regression equation against the scatter plot. Fix this typo here. So here, so I can make it easier, you are going to refer to part A. At least that's where the answer will be. So here, I'm going to take those same box points that I just did right here, these right here. I'm actually going to do it in green as well. Scroll up back to my regression plot and punch these in. You get 0.785, so that's almost 0.8. So it's 0. I'm going to put it right close to 1 there, so you can see it's in green now. And then I'm going to plot the second one, which is 1.157, so that's about a little bit halfway right there. So you can see the green points, even though they match 1 in this case, we use the same number 1. That's different from the 1, 1 that for these data that someone observed. They went and collected the raw data. And the green points, you can use 1 again to make it easy to calculate for yourself. And what happens is that it has a different result because it's a calculated value as opposed to raw data. And then you just draw the line that's between them. You can use a straight edge or whatever the case may be. I don't think I have one here, so I'm going to eyeball this. Yeah, that's good enough. Okay, so that orange line right there that I drew between the green points, that would be your regression line. And you can see it's in the upward direction. You can also see that it doesn't cover or go between the 3 points on the top and the 3 points on the bottom and the 2 points on the bottom. So something like this. So you would assume that it would do something like that. However, based on the data, it actually punched it up a little bit more. Okay, and that's probably because of outliers. Like this one right here, this seems like an outlier because the line is closer to the 3 dots right there, but this one's further out. So you don't know what's going on exactly. That's the type of analysis that you'll be doing when you're looking at graphs like this. So let's continue on. So those are generally, actually no, I lie. One more part here involves heavy calculation. So here we get part E, and this will say something such as find the correlation coefficient. Okay, this you'll find out is basically R. Find R. Maybe a lowercase r. It depends who you're talking to. Now this one has, unfortunately, a big equation as well. I'll write it down here for reference. This is n summation xy minus summation x summation y square root of n summation x squared minus summation of x quantity squared square root again and summation y squared minus summation y squared. Okay, so some things to note to make your lives a lot easier. Remember that green asterisk I did for the sum of y squared? That is applied right here. So I'll draw another, well, green asterisk right there as well. Okay, some other things to note. I'll write these in blue here so you can see. This numerator, this is the numerator of the slope. So basically this is beta 1 on the top. So I wouldn't stress out about that so much. But now we have these two square roots. Well, the first square root, if you notice, is the denominator. Of beta 1 and beta naught. So they're the same. So it's just the same exact number, 50 if I remember correctly, right? The only thing that's new is this second one right here, but this is basically the same denominator, but x for y, or y for x, I should say. So I would say same style denominator with y instead. And you can see it because it's the same exact thing with y's instead of x's. Now, the way to do this, I would personally not calculate the square roots immediately. I would write it as the following. So here, we already know this number. This one is going to be 21.25 all over square root of 50, right? I would leave it square root of 50 like that. And then I would take the time to rewrite this new portion of the denominator just so you can have it written out, which would be 5 times 25.815. So that's the number we use, minus 10.3 squared. That's all over square root as well. I know I squeezed it a little bit to the right side, but I'll move it down here. And again, I would still calculate this portion here so that it looks like this. 21.25 square root of 50 square root of, and I have this written out here in advance, what is it, 22.985, 22.985. So this is how I would have it written, and then you would do this on the calculator. Now, a big note, do not forget the parentheses in the denominator, because you want to make sure that the 21.25, or in other words, the numerator, is divided by the product of the square roots. So if you're punching this on your calculator, you want to make sure that you have 21.25 divide and open a parentheses right there. Then you'll go, and you should get this answer, 626832.749, whatnot. But basically, you're going to say that R is equal to 0.6268. And that's also read as 62.68% as well. So that's R, correlation coefficient. Okay, now I can actually say the first 5 parts, A through E, A, B, C, D, E, those are the heavy calculations right there. That's as difficult as it gets in terms of mechanical. Now the rest of this is more theoretical. You have to understand the concepts, and of course we're going to go over that as well. And I'll walk you through that as well. Now for the hypothesis testing. So here in part F, I'm going to write out the formal question. However, I'll put in parentheses saying that this is basically your hypothesis testing. Hypothesis testing, similar to that of Z and T scores, for example. Probably future videos I will make at some date. A chi-squared or an ANOVA problem. This is the hypothesis testing that we're talking about. So the question would generally say something such as, is this correlation statistically significant? And then we'll say test at alpha equal 0.05. Again, standard right there. Now basically what I'm going to say here in purple is basically you are doing a hypothesis testing for regression. So in other words, you want to make sure that your hypothesis testing has your 3 criterion which qualifies as a hypothesis testing. So that's your initial conditions, your calculations, and your conclusion, as well as an ending statement. And the parts that, at least what I learned when I was taking AP Stats many years ago, that those are the criterion that make up a hypothesis testing problem to be complete. It's similar to that of a scientific experiment, or not scientific notation, but the scientific experiment steps. There's 7 steps, right? You have to make the hypothesis and then results, and it's done in many labs. So here I'll write out the initial conditions. So what are they? In this case, H naught is a Greek letter that looks like a P, but it's called rho, R-H-O. Rho is equal to 0, which basically means there does not exist. Remember that backwards E with a slash means does not exist. Does not exist a correlation within the population. And remember, your alternative is always an opposite statement. So the alternative is rho does not equal 0, which means there exists a correlation within the population. Which seems a little funny because here you have equals 0 but there does not exist, and here not equal to 0 but there does exist, so it sounds a little opposite right there. And remember, don't forget your alpha of 0.05. That is part of the initial conditions. Now the calculations. The nice thing is that the calculations, they're done. You've taken the time to do parts A through E collectively, and you've already done the calculations. So I'll walk you through as to what they physically are. So the calculations, specifically what you're doing or what you're going to be analyzing, calculations, is this. So remember your R. R we found to be, I'll have to scroll back up because I already forgot, 6268. 6268, right? This is your calculated value. Why is it calculated? Well, you took the time to calculate it. Calculated value. Okay, and we have to use the degrees of freedom to find our critical value. Now, haven't mentioned it yet, but the degrees of freedom, and I'm going to put a little r for regression there. In this case, it's special. It has a different one. It's n minus 2 instead of the traditional 1. So that means we're going to say 5 minus 2, which means the degrees of freedom for regression in this problem is 3. This leads to a table value, and again, you will probably want to pause this here, pull out your statistical table or Google it, and you're going to look for a regression one. You're going to look at the 0.05 significance level, and you're going to go to degrees of freedom down to 3. You should be seeing a value of 0.88. This is what's called your critical value. And again, you'll hear me informally call it your table value, your lookup value, something you have to do that doesn't involve calculation. So basically, we're going to be comparing this one and this one here. Okay? And again, the calculations are not heavy in this hypothesis testing portion because you've already done it. You've done it in the previous parts. Now, the conclusion itself. Now, this one's a little bit unique because it doesn't match the exact criterion as I've taught it in terms of testing one number against another number. You're still testing something, but we're checking the following. Actually, I can type this one out. So we're going to check. We are checking the following statement. Does our R, remember that's your calculated value, misspelled it, calculated value, fall within, I probably should italicize that, fall within our table, and then that would be our critical value. Critical value. Okay, your hint here is to remember to treat this like a two-tailed test. Treat, and I'll tell you what that means in a moment. Treat like a two-tailed test. Okay, so this is what we're doing. In other words, we take the 0.88, and then you're going to make this a plus or minus, because two-tailed, right? Both sides. Then we're going to ask ourselves, does R fit within this range? How do you write that? Normally you would write it this way. Does R fit? And you're going to write it in this fashion. You're going to write it negative 0.88 is less than R, which is 0.6268. Let me double check that. 6268, yep, good. Is less than the positive version. Now this one, you have to be quite careful because you're focusing on two sides of this inequality equation. So here I'll underline. First, you're going to look at this left side right there. Is that true? Well, of course that's true because there's a negative version on the left-hand side and there's a positive version. So that's good, but it's not enough. You have to do both sides. So now we're going to double check this side now. So this is where normally students get mixed up because they'll see one portion of the inequality and they'll think it's true. And then they realize that, oh wait, it's actually both parts you have to worry about. So here, the green underlined portion, that's true. Negative is less than positive. That's easy enough. However, the right side, you got to double check closely. So saying this out loud or pausing the video, whatever case you may ask or do or say, you're going to ask yourself, 0.6268, is that less than 0.88? Okay, and you pause. And you realize, like, yeah, this is true. So this whole thing is a true statement right here. This entire expression is a true statement. So what happens when it's a true statement? When it's a true statement, we basically do the following. This implies that we fail to reject H naught. What is H naught again? Remember, you still need to make a statement about this, right? You can't simply say that, fail to reject H naught. That's not a good conclusive statement. You have to further by saying fail to reject H naught, that we reject or we can say there does not exist a correlation between what is it, hours spent shopping and USD spent. Okay, so in other words, this is not statistically significant. Right? Because what happens is that what I've described before, this black number right here, 0.6268, falls within range of our table value between negative 0.88 and positive 0.88. Depending on the regression problem you have, you're going to have different things, right? You're going to have a different R calculations, you're going to have different degrees of freedom because your sample size is going to be different, whatever the case may be, right? But the idea is that does the black number fit between the two blue numbers right here, right? In this case, it does. If it does, that means it falls in our area of acceptance or a region of acceptance. So this is expected to happen. Since it's expected to happen, it's nothing significant about it. So that means the fact that I'm going to scroll back up really quick, that it looks like the data is going to be in a positive correlation, statistically speaking, right? This is in terms of statistics. It might be true in real life in terms of everyday experience, whatever you would like to call it. But statistically speaking, it is not significant because that's what the data shows. Okay, so that's good right there. Now, if the statement is false, then you would reject the null hypothesis, and then the results would be statistically significant, just as a heads up there. So it's opposite. Okay, that was part F, I believe. Okay, now part G. We're almost done right here. 2 more parts. So part G. Normally, you'll get this kind of statement here, and this is quite important to follow along because it's a very cookie cutter or standard expression. So I'm going to write it formally and tell you how it works basically for any other problem. So here's the question. You'll either get it as this: what percent of variation in USD spent shopping is explained by the number of hours spent shopping. Shopping. What percent of variation USD spent shopping is explained by the numbers of hours? Actually, I'll just say spent right there. USD spent is explained by the number of hours shopping, spent shopping. Getting redundant here. Okay. This is also known as, or finding the coefficient of determination. They are the same thing. Okay, but basically, this is what you're being asked. Basically, what percent of the y variable is explained by the x variable, sorry. That's all it's asking. Very straightforward. Okay, and that will always be written that way, and it's kind of annoying because you're hearing the y component first before the x, which makes it's a little bit against the intuitive aspect because you study xy when you're learning algebra for the first time, or whatever the case may be, right? But basically that's what's being asked. Now, how do you calculate this? This is actually very straightforward too. It's basically r squared. So you take 0.6268 and you square it, and that's the answer. I did it in advance, so this answer is 0.3929192 dot dot dot, and basically it's 0.3929, so it's about 39%. Okay, so in other words, the way to understand this is that 39%, 39.25% almost, basically 39% of people spending on shopping is explained by the number of hours they're shopping. So in other words, they're spending, right? What contributes to that spending? 39%, 39% is from shopping, which makes you think, well, if it's only 39% that is being described in this problem, what about the other percentage, right? The other portion that makes up 100% for someone to be spending money. And that actually segues into our last component right here, which is part H, right? So here you can be asked, what percent of variation in USD spent shopping is explained by other factors? Explained by other factors. So in other words, as I was alluding to earlier, right? It's kind of like saying this. Here you have the total explanation, right? You can think of that as 100% or 1, decimal point 1, right? And 0.3929 is what we called up here explained variation. It's considered explained variation because you know what the explanation is. In this case, it's the x variable. The explained portion is the number of hours spent shopping, right? Not the dollar value, the actual hours, the hours like in the shops and whatnot. Explained variation. That we found to be 0.3929. Well, if you have explained variation, you must have also unexplained variation to make up total explanation or total variation. That's what I meant to write. Sorry. That's a typo. Make sure to fix that. Total variation. Variation. There we go. So unexplained variation. So this is the number we're looking for. This number right here. I guess I can put a purple star here. This question's asking, hey, if 39% is described by the x, what about unexplained variation? Or in other words, other variables that we have not made or have access to or even described here. So here you can actually see it's basically 1 minus 0.3929 or 100% minus 39.29. But anyway, it's this. So it's basically 0.6071. And again, I got that because I took 1 minus the explained variation. This is considered the unexplained variation. So that's it. Basically, what other things are contributing to the US dollar spent? I mean, if you really want a formula, you can think of this as 1 minus r squared. That's essentially the formula, right? That's what I did, 1 minus 0.3929. That's something to consider, okay? And then if any other questions were being asked, for example, say there was a part A, B, C, D, E, F, G, H, I, right? Though I highly doubt it. But if it gave you an open-ended question, so for example, what other factors can explain USD spending, right? That's open-ended. That can be answered by a numerous amount of ways. You could say that there was a sale, there was no sale, people didn't feel like buying this particular weekend. The sample that you sampled was more frugal in their shopping, was more spending on their shopping. You know, there could be a lot of other factors other than just the number of hours you walked around shopping, right? So if you're ever asked a open-ended question going, well, what's the other 0.6071, or in other words, what's the other 61% almost explained by? Well, you don't know because there's only one variable here, the number of hours spent shopping. But if you had to come up and make an educated guess about, well, what else contributes to people spending physical money? Well, it could be anything you want, just has to be a logical reasoning. As I mentioned before, there was a sale, there's not a sale, depends on the people you sampled. Maybe it was the mall that you're in, maybe it was where you were sampling, maybe it was a different country, maybe geographically it wasn't a very high shopping area, you know, whatever the case may be. Okay, and this wraps up a simple regression problem with multiple parts uninterrupted, and you can now hopefully see how all the parts are related. Even though there's a lot of moving parts, it is all here, and you can take the opportunity to pause and re-watch and whatever the case may be. And thank you for joining in.